We've been talking about solving the Schrodinger equation and how the potential function encodes the scenario under which we're solving the Schrodinger equation. The first real example of a solution to the Schrodinger equation and a realistic wave function that we will get comes from this example, the infinite square well, which I like to think of as a particle in a box. The infinite square well is called that because its potential is infinite and, well, square. What the potential ends up looking like is, if I plot this, going from 0 to A, the potential is infinity if you're outside the region between 0 and A, and at 0 if you're in between the region, if you're in between 0 and A. So what does this look like when it comes to the Schrodinger equation? Well, what we'll be working with now is the time-independent Schrodinger equation, the TISE, which reads minus h bar squared over 2m times the second derivative of, sorry, I'm getting ahead of myself, the second derivative of psi with respect to x plus potential as a function of x times psi is equal to the energy of the stationary state that results from the solution of this equation times psi. Now, this equation doesn't quite look right if we're outside the region. Bad things happen. You end up with an infinity here for v of x if x is not between 0 and a. The only way this equation can still make sense under those circumstances is if psi of x is equal to 0, if x is less than 0 or x is greater than a. So outside this region, we already know what our wave function is going to be. It's going to be 0, and that's just a requirement on the basis of infinite potential energy. Can't really exist in the real world. Now, what if we're inside? Then v of x is 0, and we can cancel this entire term out of our equation. What we're left with then is minus h bar squared over 2m, second partial derivative of psi, with respect to x, is equal to e times psi, just dropping that term entirely. So this is the time-independent Schrodinger equation that we want to solve. So how do we solve it? Well, we had minus h bar squared over 2m times the second derivative of psi with respect to x being equal to e times psi. We can simplify that just by rearranging some constants. What we get, minus second derivative of psi with respect to x equal to minus k squared psi. And this is the sort of little trick that people solving differential equations employ all the time. Knowing what the solution is, you can define a constant that makes a little more sense, in this case using a square for k instead of just some constant k. But in this circumstance, k is equal to root 2m times e over h bar. So this is our constant, which you just get from rearranging this equation. This equation you should recognize. This is the equation for a simple harmonic oscillator, a mass on a spring, for instance. Now, as I said before, the partial derivatives here don't really matter. We're only talking about one dimension, and we're talking about the time-independent Schrodinger equation, so the wave function here, psi, is just a function of x, not a function of x in time. So this is the ordinary differential equation that you're familiar with for things like masses on springs. And what you get is oscillation. Psi, as a function of x, is going to be a sine kx plus b cosine kx. And that's a general solution. A and b here are constants, to be determined by the actual scenario under which you're trying to solve this equation. This equation now, not the original Schrodinger equation. So these are our solutions. Sines and cosines. Sines and cosines. That's all well and good, but that doesn't actually tell us what the wave function is because, well, we don't know what A is, we don't know what B is, and we don't know what K is either. We know K in terms of the mass of the particle that we're concerned with, Planck's constant, and the E, separation constant, we got from deriving the time-independent Schrödinger equation. While that might be related to the energy, we don't know anything about these things. These are free parameters still. But we haven't used everything we know about the situation yet. In particular, we haven't used the boundary conditions, and one thing the boundary conditions here will determine is the form of our solution. Now, what do I mean by boundary conditions? Well, the boundary conditions are what you get from considering the actual domain of your solution and what you know about it, in particular at the edges. Now, we have a wave function that can only be non-zero between 0 and A. Outside that, it has to be 0. So we know right away our wave function is 0 here and 0 here. So whatever we get for those unknown constants, A, B, and K, it has to somehow obey this. We know a couple of things about the general form of the wave function. In particular, just from consideration of things like the Hamiltonian operator or the momentum operator, we know that the wave function itself, psi, must be continuous. We can't have wave functions that look like this. And the reason for that is this discontinuity here would do very strange things to any sort of physical operator that you could think of. For example, the momentum operator is defined as minus I h bar partial derivative with respect to x. The derivative with respect to x here would blow up and we would get a very strange value for the momentum. That can cause problems. By sort of contradiction then, the wave function itself must be continuous. We'll come back to talking about the boundary conditions and the wave function later on in this chapter, but for now, all we need to know is that the wave function is continuous. What that means is that since we're 0 here, we must go through 0 there, and we must go through 0 there, since we're 0 here. So, what that means, wrong color, means psi of 0 is equal to 0, and psi of A is equal to 0. What does that mean for our hypothetical solution, psi of x equals A sine kx plus B cosine kx? Well, first of all, consider this one. The wave function at 0 equals 0. When I plug 0 into this, the sine of 0, k times 0 is going to be 0. The sine of 0 is 0, but the cosine of 0 is 1. So what I'll get if I plug in 0 for psi is 1 times b. So I'll get b. Now if I'm going to get 0 here, that means b must be equal to 0. So we have no cosine solutions. No cosine part to our solutions. So everything here is going to start like sines. It's going to start going up like that. That's not the whole story, though, because we also have to go through 0 when we go through A. So if I plug A into this, what I'm left with is psi of A is equal to capital A times the sine of Ka. If this is going to be equal to 0, then I know something about Ka. In particular, the sine function goes through 0 for particular values of particular values of its argument. Sine of x is 0 for x equals integer multiples of pi. What that actually looks like on our plot here is things like this. Our wave functions are going to end up looking like this. So let me spell that out in a little more detail. Our psi of A wave function is A times the sine of K times A. And if this is going to be equal to 0, Ka has to be either 0, plus or minus pi, plus or minus 2 pi, plus or minus 3 pi, etc. This is just coming from all of the places where the sign of something crosses 0, crosses the axis. Now it turns out this is not interesting. This means psi is 0 everywhere, since the sign of 0 is, well, sine k times a. If Ka is going to be 0, then everything. If Ka is 0, k is 0. So the sign of k times x is going to be 0 everywhere. So that's not interesting. This is not a wave function that we can work with. Another fact here is that these plus or minuses, the sign of minus x is equal to minus the sign of x. Sine is an odd function. Since what we're looking at here has a normalization constant out front, we don't necessarily care whether there's a plus or a minus sign coming from the sign itself. We can absorb that into the normalization constant. So, essentially what we're working with then is that Ka equals pi, 2 pi, 3 pi, etc., which I'll just write as n times pi. Now if k times a is going to equal n times pi, we can figure out what, well, let's just substitute in for k, which we had a few slides ago was root 2m capital E over h bar. So that's k. K times a is equal to n pi. This is interesting. We now have integers coming from n here as part of our solution. So we're no longer completely free. We in fact have a discrete set of values. Now a, that's a property of the system. We're not going to solve for that. M, that's a property of the system. H bar, that's a physical constant. The only thing we can really solve for here is E. So let's figure out what that tells us about E. And if you solve this for E, you end up with n squared pi squared h bar squared over 2m a squared. This is a discrete set of allowed energies. And I'm going to put an exclamation point there because this is important. This is the quantum part of quantum mechanics. We started with a system that by all respects was continuous and had nothing really discrete about it. And what we ended up with in the end was a discrete set of allowed energies, a discrete set of solutions. Our wave functions look like psi sub n now. We don't have just any possible value, and they're going to be big A, a normalization constant, times the sine of, and if you substitute all of this back in, Ka is n pi. What we end up with is n pi over a times x inside our sine function. This is our wave function. The spatial part, our solution to the time-independent Schrödinger equation. There's only a discrete set of them, and that's interesting. That is the quantum in quantum mechanics. One more detail to nail down here is the normalization. We know the integral from minus infinity to infinity of psi star psi dx has to equal 1. Well, in this case, we know that's going to reduce to the integral from 0 to a of psi star psi, where I should write it here, psi n equals a times the sine of n pi over lowercase a x. So I can write down psi star psi now, and that's going to give me a squared sine squared n pi over a times x, integrating dx.